Okay, good morning. We have several students decide to join us online, so today I have to go slower than normal because from a remote, and here there's some whiteboard demonstration will be really difficult. So I have to transfer that into the online version and see how I use my finger to illustrate those points. Just make sure everybody online can hear me.
Yes, doctor, we can hear you. Yep.
Okay, good. So as I said, linear algebra is most important topics if you want to go into data science or machine learning. So today we are going to touch on the vectors and matrices, and all the operation on them are related to the linear algebra, and that's a foundation for everything. So this first hour we will spend the time on those basic concepts. For those from a data science background, the next hour will be 10x genomics and the pipelines. How can you get from a sample to the data, raw data, to the sequencer, and to the matrix? Okay, so that's a half-half mixture. So I want to guarantee people from different backgrounds get what you really need. Okay, so that's key point you will be taking home and after this lecture. So you need to know at the end of the lecture to know how to do matrix multiplication. Okay, what that means in terms of the general concept and also applications in single cell study. Another is geometric interpretation of matrix vector multiplication. So if you use a matrix to multiplicate a vector, so if you didn't know that before and after the lecture, hopefully you can explain that in your language, in your own language. And then I hope I can explain this eigenvalue, eigenvectors in a clear way. Everybody understand what's significant, what that means. You may heard about this. If you from a data science, computer science background, you certainly know some of this idea. And I just want to put in the biological single cell study and what that means and how can you use it later. As I said, later I will tell you how can you prepare pre-process 10x genomics single cell RNA-seq data, okay? You load your sample and in the machine, you have a droplet prepared and sequenced and what to do next. What you will get are the FASTQ files. And then you should have a standard procedure and the principle of those procedure, why you're doing this, what are each steps, mapping and the base calling and whatever. Okay. Any questions? So the most important, I emphasize again and again. So linear algebra is necessary for machine learning, everything important. Good. And to illustrate this, I switch this to Twitter. So that's my Twitter account. One of this guy I followed, he's an evolutionary biologist, statistician, and this data science people. He pretty convinced, linear algebra is basically the most important math. You can now combine linear algebra with just a touch of calculus. and you have got so much power. Okay, it's not only my own view, it's when people know this, they generally agree with me. So I just use his Twitter as one of the evidence to convince you it's important. And then for important like this, we need to have an idea about the data points. Okay, when you do experiment, you collect data points. What that means, if you think about each cell is a data point, then this data point is defined by the cell's expression, gene expressions, profile of transcriptome, right? When you have more than one data points, you collect the information from more than one cell, you have a population cell, then you get this cloud of data, right? So you get these multiple data points. When you have a group of data points, you want to know the relationship between individual data points, or you want to have a global view of your cloud of your data points. And how can you do that? One way is to look at the data from a different angle. Okay? I look at object, and from this angle, from that angle, at the end, I will have a comprehensive imagination of the data cloud and the shape of the cloud. So in order to view the data point from different angles, so you have to rotate them. You rotate the data points is equivalent to rotate the coordinates system. So in this two-dimensional space, you have x-axis and y-axis. If you rotate the data point, the same as you rotate the axis, you rotate your x-y axis from different angles. Why is it important? If you, for example, this is a hypothetical example. If I have a website like Amazon.com, but it's very special, it only allows you to produce, upload one picture of your product. Say I'm going to sell my teapot like this. I only allow to give one picture of this teapot. So I have to select correct angle, the best angle I can tell the buyers, and then what this teapot look like. So I want to turn my camera from a different angles. You don't want to do the top down or bottom up, or from the very front. Normally, I will pick some angle like this, right? If I only allow to upload one picture for my product, I want to display the largest variance for the data points. So if you think about the surface of this teapot, a mixture, a collection of all the data points. So you want to display display the longest variance, the largest variance among data points. So that's why at the end you choose this angle, because this angle tells you the most important feature to display most features of your data points. Okay, all this operation rely on you manipulate, understand this coordinate systems. You have to have a way to describe your data points. Depends on how many dimensions you want to play with. On your left is a two-dimensional space. On your right side is teapot, three-dimensional space object. in single cell, because we collect for each cell multiple genes information. So normally we have thousands of, more than thousands of dimension. There are many good books on linear algebra at different levels. So those are the lists. Then on YouTube, you have a lot of online materials, and Wikipedia resource, and a lot of blogs, articles can help you to understand some points. If you have trouble, Google them, and normally you have a good answer. People discuss, say, okay, why TCA can be done through SVD, for example. A lot of people will discuss those. Okay. We separated data points into different format, like scalar, that's a single number. Okay, if you have a number 1.2, that's a scalar. If you have a multiple scalar combined into n by 1 or 1 by n, that's a vector. And in data science, we call each data point a vector. A vector is a description, a numeric description of your data points. When you have multiple data points, so you have a collection of different vector of the same dimension, you can form a matrix, either by column or by row. Those are the matrix. So matrix is a collection of vectors, or matrix is collection of data points. Okay, so a vector, for example, this data point A, well, you can describe this using this in two-dimensional space. So you have a XA, YA. So you put it into a two-dimensional space, and then you need to have a original point like 0, 0, right? And we can put a vector like this to point to your data point. So you have an A, you have a coordinate. Similarly, if you have a B, you have 2 points. Okay, they all start from origin 0, 0. Here you have a data point X vector, and this is n dimension. N dimension, so you have a x1, x2, xn. And here is n equals 3. So you have x, y, z, axis 3 coordinates. And this is example of n equals 15, right? So you have your x1, x2, and in that way, we just cannot illustrate, use three-dimensional, and because we don't have the capacity to visualize anything beyond dimension 3. So you can plot this information using this bar plot. So x1, the value is this, x5 have the highest positive value, x6 is negative value. So you can present this as a vector. Okay, so far this is very easy, right? Okay, you have a n dimension, that you have a data point on this space, characterized or defined by n numbers. Those numbers tells you for each coordinates what's the position for this data points. And then we are going to do some operations on the vector. We can multiplicate a vector by a single number, a scalar. So in that case, you make this vector scaled, okay, by certain value. And you can do addition. So if you have two vectors, then you do addition that have a special geological meaning. We will discuss the length of the vector. So that's the distance from your data point to the origin. How long this vector is. We will see what is inner product of two vectors. By the way, sometimes you see, okay, I can define a vector by 2 points. That's from a P to Q. This is not a standard way to define a vector. So you have to move this back to the origin. So you use one of the points, in this case, the P will be reset at origin. So this vector actually is this right bar. Okay, so vector supposed to start from an origin to a data point. We don't, in some cases, if you use two data points to define a vector, so you need to transform or somehow give the correct let's see, would be correct shift of the position to give you the correct value. Now let's look at the addition and the subtraction of two vectors. So so easy. So you have A and B. A is 3, 4, B 7, 2. The summation, the addition of these two are 10, 6, okay? So when you add 2 and you actually get this, a new data point. Subtraction, if you have a 3, 4 minus 7, 2, and you get -4 and 2, that's this vector. And if you use B minus A, you get 4 and minus 2, and you get a vector of this. Okay, they are same length at the end, but a different direction, the opposite direction. Okay, no questions so far? So good. Okay. It will be easier later once we work out the matrix multiplication, then you will know how to do this inner production of two vectors. But for now, we just quickly lay out some facts. Okay, so if you have a vector, so this one multiplied by that one, there are two different ways to do this multiplication. You have to transpose one of the vector. So because right now it's the vector is a column based, you have to transpose one in order to do the multiplication. You can do, there are two ways to transpose. You transpose this, or you transpose that first. At the end, the inner product is to transpose, and then at the end, you will get a scalar. So for example, if you have two vectors, it's in the 3 dimension. So in this case, you transpose A from the vertical to the horizontal. At the end of this product, you get a single number. This is called the inner product. So you reduce the dimension of 2 into a single number. So this number has exactly the meaning. We will mention this later, okay? So this value is the product of this length of these two vectors times cosine of this angle, okay? So don't worry about this. We will discuss this more next week and also later. After you do the matrix multiplication, you will see, okay, why it is like this. Because you can think the vector are a special case of matrix. It's only because one of the dimension becomes one, the matrix reduced into a vector. But if you know how to do the multiplication for two matrices, you will know how to do this for two vectors, because vectors is just special case of matrix, right? So don't worry about this. It's an important relationship, but it needs some time to digest. So I skip this, leave it for later. Once we will come back to explain why it's true and why it's important. Okay, now we're talking about the norm of a vector. I don't know in the classroom how many of you heard about the norm of vector. No, no. Alex, no. Okay, so you from EC, right? Okay, so we have one student from engineering background. He knows. Okay, all the people from a biology background have no idea what norm is. Okay, so if you have a vector, see, it's n dimension. So you have x1, x2, x3 to xn. Now let's just think about this at n equals 2. So in this case, you reduce your norm definition into something like this, right? Only 2. So what it is, x1 squared plus x2 squared and the square root of the sum. So that's a norm. In this case, you have a 3 dimension, 3 as an example. So the point of this data is a 3 to 5. So you do 3 squared, 2 squared plus 5 squared, square root. This is called the norm of your vector. It is the length of your vector from your data point to the origin. So how far away, right? That's a distance, okay? So the norm of a vector means how far this data point to the origin. This Frobenius norm is for the matrix, okay? So same idea. So another important concept is this so-called unit circle. So this is a circle around the origin, the point, with all the point on the circle has the norm to the origin equal to 1. Okay, any point on this circle, any point is a vector. Okay, in this 2 dimension will be x and y, 2 coordinates. The distance from this point to the origin, which also the norm of this vector is 1. So every point on this circle have a length of equal to 1. So in this position is right is 1, 0, and this position 0, 1. This minus 0, right? And so if this 45 degree here, this point will be 1 over squared. So, okay, this point in the 45 degree, for example, here, the coordinates will be 1 over square root of 2, okay? 1 over square root of 2. Then if you square this, square that, take a sum equals 1, and the square root, the norm of this equals 1. So you can find the position, and also you can define this position here by using sine and the cosine value. If you are given the angle of the theta. Okay. So there's circle. If it's a 3 dimension, you have a sphere, okay, right? The unit sphere. Again, this is called a unitary operation, and that's all the operation on working on the sphere, for example, working on this circle. Okay, let's see the time. Now we jump to higher dimension from a vector. There's n times n by 1 or 1 by n. Now we have a n by m or m by n. So n and m are greater than 1. So in that case, you have a matrix. We have those operations. Okay, normally we in data science, people use vertical vectors as the data points. In statistics, people use rows, okay, horizontal vectors to present data points or sample points. So you need to make clear, you should know whether your matrix is a collection of the data points, it's a collection of vector. You need to know whether it's column-based or row-based. Otherwise, you opposite this data points and its feature. You don't want to use variable to replace the data points. To convert from a row matrix to the column matrix, you use this transpose, which is do this operation. Identity matrix is all the diagonal elements are 0 and only this diagonal line element are ones. Okay, this in this case is a 4 by 4 identical matrix, or you can have a n by n squared identical matrix. So matrix can be doing this element-based addition operations pretty easy. So you can do this just like numeric scalar. You can scale a matrix by multiplicate by a factor. In this case, you multiplicate a matrix by factor 2. In that case, every element in there and multiplied by 2, and you have the end product of this. And there are some properties of scalar and the matrix multiplication. Easy, right? So far, okay. Now we are going to move to matrix multiplication. So those are the definition I copied from a textbook. I'll give some examples. Those are not really good examples. And so I'm going to give you a real application, a daily application of this. So imagine, and that's you and your roommate. You decide to make some sandwiches. There are 3 types of sandwiches. 1, 2, 3. You want to make 4 type 1 sandwich, 5 type 2 sandwich, and 3 type 3 sandwich. Okay, and your roommate, you want to make 3, 3, 6. So that's your matrix A. Well, these 3 sandwiches, 1, 2, 3, are made from the combinations of different ingredients. Like you need 2 slices of bread for each. You need 4 ounces some peanut butter. So that's pea and jelly. You have a slice of ham and a slice of cheese and a slice of tomato. For sandwich 1, you don't need ham, cheese, or tomato, but the sandwich 2, you have this different combinations. So that's your menu to make the ingredients combination. So now my question is, if you want to make this many sandwiches, how much of each ingredient you have to prepare? And that's the multiplication of A and B 2 matrices. At the end, you need in total 24 slices of bread. If you move down, you need 6 slices of tomato. Your roommate, you need different numbers of these combinations of those. Okay, so that's the meaning of matrix multiplication. At the end, you get your product. It's a collection of different components. You want to make some it's a sum of these gradients. You want to make, in this case, three sandwiches. Now you can replace this. Instead of using sandwiches as an example, I can replace, for example, you as one type of cell, and your roommate as another type of cells. And these gradients are the different genes. Okay, you need different genes combinations, expression combinations to make 1, 2, 3, 3 different biological programs. So if you convert that concept into some single cell related topics, you can imagine and see, replace that. At the end is the matrix you observed from a single cell study. For example, you know your cell type Y and cell type R have a gene expression level of B, P, J at that level. That's your observation. However, you should be able to decompose it into 3 different programs. The single gene, for example, bread gene, involved in all 3 programs. And the gene tomato only involved in program 2 and 3, because only in 3 program according to this. Well, I really need to have a let's see, how can we do this? I need to give you a way to see how can we do this multiplication. Give me 1 second so I can write this number down. Then I'm going to use the whiteboard, I mean the online whiteboard, to illustrate this, okay? This is very important, so that's why I want you to get it done. And let's see, I will range my A matrix here. Well, okay, my A matrix 4, 5, 3, 3, 3, 6. Okay, so this matrix is a 2 by 3. That's dimension, right? In order to multiplicate by another matrix has to be 3 by something else. In this case, 3 by 6. So that's called the inner dimension has to be matched. Let me see. Okay, so that's the product. So I have to do, this is 2, 2, 2, 4, 4, 0, 0. Okay, so I arranged these two matrices in a way that at the end, so you see, I put this 2 by 3 here and the 3 by 6 on the top. The reason I want to leave the space here, so I know at the end I will get a product. The dimension of this will be 2 by 6. So you see, I leave this space, the square, rectangular here, white space. And then the next, I'm going to fill in those 4 2 by 6 values. So this first value will be the column here, the row here, and the column here. And they multiplicate 8, 10, 6. So that's 24. So that's 4 times 2, 5 times 2, 3 times 2, and then sum. That's your first value. 24 here. Okay, because this inner product dimensions 3 and 3 matched, so I can do this. Otherwise, you just cannot compute. So the next, I'm going to do, for example, this one and that is also 24. So gradually, I fill in all the 2 by 6 element. That's my matrix, 2 matrix multiplication. Put them into the correct location and define this empty space of white space, so you know the end product will be the correct dimension. Then you start to fill in the values. Okay, I hope everybody get this, because that's the most important point we want to make. If you forgot everything else, know how to do this manually. Okay. Online students, are you okay? Now, if I gave you 2 vectors instead of these 2 matrices, for instance, if you do a vector 453 times 222, so 2 vector multiplication. Vector vector 453 Can you do this as the same, using the same principle, the same way you do the matrix multiplication? I will see there are two ways you can do. First, you are going to put V horizontal. So you have a 4, 5, 3. And then I will arrange 2, 2, 2 here. So what's the end product, the dimension of end product? That's right. So because you have a space here, it's 1 by 1. So in that case, this 2 vector multiplication as a special case of your matrix multiplication, you get a single number, 24. The dimension is 1 by 1. I can also do differently. I can see, okay, I will put 4, 5, 3 here. Instead of make V horizontal, I make U horizontal. In this case, I will have 2, 2, 2. So anyone tell me what's the dimension of this product of two vectors? Can you do that? That's correct. The answer for this product is 3 by 3. So you fill in this 8, 8, 8. Okay, the product of two vectors, this is called inner product. So what should we call this? Outer. So inner product make a scalar 1 by 1. The outer product expand this. Okay. If you can get this, I think today the first hour we are okay. We know how to do matrix multiplication, matrix by matrix, and use vectors as a special case. So you know, okay, you can multiplicate a vector by another vector in two different ways, inner product or outer product. And you can also multiplicate a matrix to a vector or a vector to a matrix. Questions from Alex?
How do you decide which one to use, inner or outer?
Yeah, so there are different scenario, and you will know later.
Okay.
Yeah.
So because I thought you could only multiply the two vectors if they were similar to matrices, so that only the first one was 1 by 3, the second one was 3 by 5.
Yeah. So you have to have a same dimension. So
right.
Yeah, that's right. So if you have a vector, say 2, 2, 2, 4 is one dimension longer than another, they cannot make it.
Right. So does just rotating them like that, does that not change any of the properties of the vector?
Yeah, you rotate one matrix, one vector, and multiply it to another. And in this case, you are doing the inner product.
Okay.
Yeah, they're
So we're allowed to just do that in a sense?
Yeah, there's another way, actually, if you do element-based V times U, so you have a this times this times that times this. This element-based is another way to do multiplication. But in lineage algebra, we use inner product most. So I put a yellow star here. So that's important because now you know how to do this matrix to matrix multiplication. And also you have this example on your mind to know, okay, what that mean? So when you multiply one matrix to another, then you actually compute this. the gradients you need for different set of these combinations. Okay. So now another question for you to think is, if I only gave you the end products, say A and B, AB product, this matrix, would it be possible for you to reconstruct the original A and B? So when you do the multiplication, it's actually very easy. You know A and B, the AB product, you can compute. But if I gave you AB product, would it be possible for you to decompose it into A and B? For example, you and your roommate go out to the grocery store, you buy 24 bread, your roommate buy 24 bread slides, you buy different numbers with jelly and the slice of tomato. Would someone else could have figured out what you are making in your dormitory?
They would have to know how many different sandwich types.
Yeah, they would have to know what it makes.
Yeah.
Yeah, so you need to know some kind of K. So how many sandwich you want, different kinds of sandwich you want to make. So that's a critical information. So that K means the number of components. You know, okay, your system has some components, but it's not an infinite number. You want to know. But if you know this recipe, you know one of the matrix, it will be very easy for you to compute the other, right? That's nothing. But in biology, in single cell study, you get the product A and B. That's your observed matrix. However, you don't know how many programs this gene involved, and you don't know each cell how many biological pathway is active in there. So you have this so-called blended A and B. So you have to do this. Would that possible? So we will have a lot of those problems, right, at the end. So you know how to do the multiplication forward, but when you want to do the backward, it's called a decomposition. That's the big topics, and we are going to touch on those later. This is called, their algorithm called non-negative matrix factorization. NMF exactly doing this. Okay. Today we are not going to talk about it, but you have to put that on your mind. That it will be very useful if you know how to decompose a matrix. Okay. So matrix vector multiplication is a special case. Just another one of the matrix becomes vector. So you use the same rule I just told you, then just put in the correct space and not this one. So you remember how I put this and make sure you know how to arrange them. Then you should be able to do vector times multiplied by matrix or matrix multiplied vector, right? It's just special case of the matrix multiplication. Okay, let's see. Okay, we will look at this example, then we take a break. Now, imagine you have a scenario which is a data point. So X is in the position 1, 2. It's here. And I see, okay, can you multiplicate this vector by a matrix A? So you will do so let's see, okay, 1, 2, 2, 4, and 1, 2. Let me use this. So that's 1, 2, 2, 4. That's my matrix A. And multiplying my data point. Can anyone tell me what this number should be? So in this case, it's a 2 by 2, 2 by 2, and a 2 by 1. So at the end, you should have a 2 by 1. So this value should be 10, right? Okay. So if you think this as a point in the space 2, 1, and this operation is an operator that gives the transformation for the data and make a new data point after multiplied by A. And the new data point is in 510. Okay, so you see this original point is here, and at the end, the end product of this product, the multiplication after multiplied by A, and then this point become 510. I tell you, this is a special case. Normally, you don't expect these 2 points on the same straight line. This very special case means the multiplication of this matrix A did not change the angle of original point, only change its norm, makes it longer, but it still keep the same direction. You can choose other data point. For example, 1, 1, you multiply it by this, you will see, okay, not only the scale change, not only the norm, but also the angle. That's a regular case. Normally, most of the data point after do this, you will have both norm change, the scale change, and also the direction change. So this special case, 1, 2 become 5, 10, you have 5 times increase of the norm. This 5 is called eigenvalue. Okay. The eigenvalue for the system of A. So 5, which is so-called eigenvalue regarding to the matrix A. If you think matrix A is operator, it's a do something to all the data points. So it's some kind of machine, a rotating machine. Rotate all the data points because you can multiply any given data points with A. Regarding to A, the X, this 1, 2, X, the point is called eigenvector. Eigenvector is a data point. And the 5 is eigenvalue. So you have a 1, 2 data point, eigenvector, and its corresponding eigenvalue 5. So this pair of eigen describe what the A matrix behavior is. It will take some time to digest, but for now, for you is, you know how to do the multiplication. If I gave you matrix A and I gave you data point, any data point with 2 numbers, you know how to compute the product of this. And also you can see, okay, if I do this special data point, 1, 2, I will get a pure scaling effects of this vector, the length, not a rotation. So only change the scale. So that's all for now. And we will discuss this later, spend a longer time to do it. Okay. Yeah. Any questions before break?
So is an eigenvalue only exists in the context of a particular eigenvector?
Yep. So eigenvalue and eigenvector always appear as a pair of this. So you have to have a vector which is a special vector, and then with its eigenvalue together, you describe the property of your A matrix. Yeah. Alex? No. Okay, just try to figure it out. Okay. So we use eigenvalue and eigenvector. Eigenvalue is defined a point, a data points, and the eigenvalue is after the rotation, what the scaling factor is. Use a pair of this eigen to describe indirectly what's going on for this matrix A. Okay, you have to get your head around. We're not directly described what A is. A is just a squared matrix, but we use special data point and special eigenvalue linked with this data point to describe the A matrix feature.
Eigenvectors are property of the original matrix.
Eigenvector is this special data point X.
When you say describe the original matrix, do you mean they can be used to decompose matrix?
Yep.
So is that eigenvector given?
No, their algorithm you will have to use if we are given the matrix A, we want to compute its eigenvalue and eigenvector. So their algorithm to help you to do this.
You don't need matrix X to do that.
That's right. We can compute if we are given this. So for instance, Okay. So this algorithm will help us to find eigenvalue, and that's eigenvector, the last column. And this vector is normalized, so the length will be 1, but the direction will be the same as 1, 2. Okay. Well, let's take a 5 minutes break. Come back. I don't expect you. Yeah, I don't expect you have just one lecture to get your head around all this. But that's gradually you will figure it out. Okay. Yeah.
So we're scaling without rotation, right?
Yeah, we're scaling without the rotation. We're scaling by 5, and the data points, the vector is 1, 2. Okay. But here we use this unified, normalized 0.442, 0.8944 as just give a circle direct to this. The same as to remember our this point 1, 2, and the circle is so this answer is
I have a real quick dumb question. So whenever we see lambda, that's going to represent the eigenvalue.
yeah, that's this. Yeah.
Cool.
In the diagonal line here, 0 always is an eigenvalue, but it's not very useful, so people just ignore it. So when you see this D matrix, you look at the diagonal 0 and 5. And this column, the first column corresponding to the first eigenvalue, and the second column, V here, corresponding to the second eigenvalue.
Awesome. Thank you.
Okay, 5 minutes break. We will come back. Okay, so I'm going to iterate this a little bit more before we move to the experiment part, because this is important. If you try to figure out yourself, may take a longer. So it's a shortcut for you to get this idea. And the rest of them, if you just read the tutorial and read the slides, you should be able to figure it out, right? So for for any given matrix, this squared matrix as a matrix, example here, most of the data points, like this 1, 1, this is general. So if you apply multiplication of A onto it, so now we treat A as an operator, is something to impact on the data points in the space. So for the general data, you will get effects of the scaling and also rotation. So for example, if you apply A to 1, 1, and you get 1, 6, what's the value here? 3, 6. So there are scaling effects and also rotation effects. But there are some special data points, like 1, 2. When you apply A onto it, there's no rotation, only scaling. Okay, those special case, we collect them and use those as eigenvector and plus their corresponding eigenvalues. We can describe the property of A as a rotation, as a rotator or not, as an operator. So once you have this, you know how people write this. So that's A multiplied by X, any given value data point. The product will be the same as a constant lambda times X. So you can put the matrix in, and this put 1, 2, and this put 5, and you know, okay, this equal, right? So now just remember this, why we are using this. I'll show you. Okay, if I'm given a data matrix, in this case, we have n cells, maybe p genes. So that's n by p, UMI matrix, cells. What I'm going to do first, I will compare each cell by pairwise. So I will compare cell 1 against cell 2, cell 1 against cell 3. And once I finish the pairwise comparison, I will have n by n matrix. So this is a similarity matrix. Similarity between cells. The similarity is defined by their profile. If the two cells look similar, you will have a small, larger similarity. So fill in this. Okay, now I will consider this as matrix A. This is my matrix. So that's from the raw data, the data matrix. And by compute the similarity between cells, I get a matrix, which is a squared matrix, squared similarity matrix. Now, if I know how to compute this relationship, A times X, lambda times X. Right? If I have a squared matrix, I can immediately compute these two values. One, X is eigenvector, lambda is a value. This is a vector. Now I can decompose A into x minus 1 times lambda x. I just move this from the right to there. So in this case, lambda. In this case, I decompose A into 3 components. It's a vector transpose. No, this is not a transpose. This is a inverse. Okay, the vector inverse. And then I can decompose this into 3. So this will be useful later for a lot of properties to describe this A matrix. So this is one way to use this eigen decomposition. We will come back later once we start to use eigen decomposition. Why? Once we have this transformation and those products can be some meaningful coincidence. Okay. Okay, I said inverse. I just told you, and we need sometimes to compute the inverse of the. So if a number, the inverse is a number. Okay, 1 over something. But in the matrix, once this n is a matrix or it's a vector, the inverse is slightly different. So you have to find A inverse matrix. Their product is identical matrix. Sometimes it's easy and sometimes it's not so easy, but numerically people have algorithms developed for those. So we just call functions. In MATLAB, for example, I can do the inverse of something pretty easy. V of A will be then this times A itself. Inverse of A. I don't know if I have to normalize it. I don't know. Well, for some reason, because it's a. Oh, so there are some conditions and you cannot do the inversion of this matrix A. Yeah, so that's why I use a pseudo inversion, but it's not a real inversion. And for this case, we don't have answer for this inversion of this. Okay. So if I do an inversion of this, I should be able to work it out. And the B times inversion should be a identity matrix. Okay. So we need to have a way to figure out which matrix have inversion of itself and which one shouldn't have. So this is called, if it's invertible, so it's called a non-singular, and otherwise, is that the problem with a singular matrix? So we don't have inversion. Yeah. So we just had a singular matrix. We don't have inversion. Okay, the trace means you extract all the elements in the diagonal position and sum them. I think I will skip this determinant because we don't usually use them a lot. They are very clear geometric interpretation of the determinant, basically the volume of the matrix indicated. There are okay. You see here another yellow star, and it's important. I hope you can understand at the end. So when you do the eigen decomposition, basically you want to try to find eigenvalue and eigenvector. Just every eigenvalue and the eigenvector will always appear as a set. Okay, you want to find that for a squared matrix. So A has to be squared matrix. That's why if I have n by p matrix, there's no way I can do eigen decomposition. I have to convert it to a n by n matrix, the squared matrix. Then I can do this. Okay, so this set, eigenvalue and eigenvectors, is a way to get at the geometric characteristics of a squared matrix A. What does this linear transformation look like? So now you should have a way to think, okay, this matrix A, not only just like we did the sandwich example, not only just count a number of how many slices of the tomato, how many pieces of the bread you want to buy. But in this case, you think a squared matrix as an operator. This operator applied to data points in the n-dimensional space and rotate them and scaling them. Okay. Okay, so that's the same as we illustrate, just use the whiteboard. Another example, we use some different numbers. In that case, this, and you have two eigenvalues, and each corresponding to different eigenvector. Okay. You can try and see, okay, whether this relationship hold. Okay, that's how you can find eigenvalue and eigenvectors manually, okay, by hand. For 2x2 matrix, small matrix is possible. If you know some of this, how to compute the determinant, for example, you will be able to compute this. And you can validate using the MATLAB or other eigen functions. That's one of the usage of decomposition. So here, as you see, I decompose A into eigenvectors and this lambda and eigenvalues. Why it's useful? In this case, it will be very useful to do this, take the power. So for example, if you want to compute A times A times A, that's A cubic, or this 2 the power. It's numerically expensive, it's hard to compute. But if you decompose it, then you don't have to compute those S again because they all cancel each out. You only compute a single number here and to a square or to n power. And then you get the answer for A squared A or n power of the matrix. So it's kind of using the decomposition, eigendecomposition, to compute the power of the matrix. Okay, we will have other applications on during the course later, and now we move to once you have a single cell raw data, what you will do with them. You see this before, and the controller capture individual cells and do the PCR polymer chain reaction, okay, to amplify those mRNAs, and then label it with the tags, okay. So that's a machine, and that's the illustration of the GLBs. And some of this quality control, you want to load the cells without this samples, without the bubbles, right? You want to keep as many live cells as possible. Treat them gently and dissociate and check the viability before you load onto this plate, right? I hope you can explain those now, right? Last time, that's the most important point, last lecture, the principle of this barcoding system, why it works. You have a 10x barcode, this oligo, and for each gel bead, and then there are unique combinations of UMIs. So this part is shared for all the gel beads for the same bead, but this part is unique. Each of this orange one is unique. That's why any mRNA linked to here will be amplified, labeled with a particular UMI. Later, you will collapse those PCR biased amplification into just one. So each mRNA just count once. And also the barcode tells you which cell it comes from. I think that's a preparation for the sequencing library. So once you have this gel bead and then captured all the mRNAs, then you will break up those droplets and put them together and to amplify, then send it to the sequencing Illumina sequence to do the large scale deep sequencing.
So if you don't want to sequence other type of the
mRNA, RNA. Yeah. Yeah, so RNA is a highly diverse molecular species. You have different kinds of RNA. You have a long non-coding RNA, you have a microRNA, different types, but we have to focus on the most important ones, is the poly-A-tailed protein coding genes, right?
Yeah, I mean, if we want to phenotype other types of we have their specific sequence that we can recognize.
Yeah. I think if you have a special requirement, say, I want to study a particular family of long non-coding RNA. There's a way in 10x genomics solution, they covered some of this antibody tags onto the surface of those, so you can somehow enrich this particular mRNA you really want to study. You have to have other different ways to change this poly-T tail to something else. You tag it with some.
The antibody is one.
Yeah, I think so. There's solutions for example, you really want to have a T cell receptor and the genes to be amplified. There are special treatment of this, and to let you to do one more step to enrich this particular types of mRNA or other type of RNA. It's possible, but not the you may have to have a customized solution for that. It's a good question though. But for now, we only focus on the poly-A-tailed mRNAs. But in real applications, we see long non-coding RNA, even though we don't think they have a poly-A-tail, also you get enough rates. For example, there's one long non-coding RNA called the MALA1, and it's take a lot of the rates to get its expression level. It's because it's so abundant, and the 10x genomics people really want to get rid of those non-specific binding. Okay, so that's in, so once you prepared this in Illumina sequence, you have a pair of the primers, then you will sequence everything in the middle. Okay, you will sequence the barcode base pair. So in your rate, you will get, okay, you know which cell it comes from. And you have UMI, so you know, you count them just once. And then this part, you have some gene transcribed body, and so you can relocate which gene this transcribed was transcribed from. There are some details because you work on the on these combinations of sample index. The sample index is from Illumina. Illumina adds its own, and then you have another layers of this text, you know, in the barcoding system, and you have UMI. So that's the numbers. Yes, so the length to be enough to tell, to separate samples, separate cells, separate genes. Again, that's the illustration. Illustration with read 1, the read 2, and the cover different regions. And this called pair end sequence in the Illumina. And because they have Illumina index, so you will know read 1 matched with, paired with read 2, and the read 2 gave you the information of the gene and transcript. Read 1 gave you the information about UMI and the text barcode. So there this pair end systems in Illumina system, so make things a little bit complicated, but at the end you get something like this. That's from the barcode library. And that's the original version. I believe you have 16 base pairs of each of this is a unique sequence for 10x barcode. So that's the top of the file, and that's the end of the file. So I open this and look at them. There are 737,000 of this. Okay, so that's enough to tag cells. Normally we target on for 10,000 cells. So that's more than enough to label every cell uniquely, right? And the UMI, so next will be the 10 base pairs. That's version 2, and in version 3, they increase 2 base pairs. So you have a 12 base pair UMI barcode like this. Also, there you have a library. So once you sequence, and you recognize, okay, that's the UMI position and what the UMI the sequence is, and something like that. Okay, so once you have the data come from the controller, and you will load the sequence data out, and then use cell ranger. So that's all the 10x genomics software solutions. We don't have a direct contact with any package inside controller, but we use cell ranger as a standard software solution to convert FASTQ, the Illumina rates, into UMI matrix. And they also provide this browser, and this is a the downstream, the desktop solutions. You can try if you like, and certainly we have our own solution. Remember, we have the MATLAB-based solution. I just made this MATLAB-based solution standalone. So right now you should be able to run on Windows machine, even you don't have MATLAB installed. Okay, I just make this possible. Still, we have to use this solution. There are alternative solution, but this one should be okay. So what's inside this pipeline, cell ranger? It's Linux based, so I have no way to show you on my laptop. I have to link to a Linux server somewhere. The clusters will be good. And that's steps. So you start to recognize those sequence and the barcode and separate it into by cells, by genes. Then internally, there's a liner called start. Start is a Linux, again, Linux-based tool. This aligner is to get this piece of DNA fragment and map to the gene it come from. So to align it. Then once you align, you count which gene, the expression level, and then you make this gene cell matrix. That's normally we will do the downstream. Okay. Okay, from the Illumina, you will get 3 rates files. One is R1, which is the pair-end system, so you have 2 rates files, and then R2, and this is the index file. So that's the file looks like. 3 files, and here are your sample name, so you know it. And this length and the indicator of the 3 files. These are the Illumina machine. And if you have multiple samples, you load balanced into different lengths. And they all are zipped. So you have. Okay, in Cell Ranger, this command line, you see account, ID, and that's my reference. Because you have to map your arrays onto the reference. This is a human genome, and also the transcriptome information should be there. That's a folder, and that folder has been prepared by using some of these different commands. And then you provide your sequence folder. So you have 3 files, FASTQ files in that under this folder. And then you define how many CPU cores you want to use, how much the memory you will take. Okay, the program will look at the cells, which by this barcode in different colors, and then look at the UMI. So it's unique, and which gene. In this case, for example, this gene, there's 2 fragments mapped onto the same gene. So this gene has maybe two copies. But because they are the same UMI, so we only count them once. Okay, because we think that the system considers this as the same mRNA was amplified multiple times by the PCR reaction. So we want to collapse this. Rather, this is mapped to the same gene, but you have a different UMI. So that's the same gene have multiple copies in the real system. So we count them twice. So at the end, we don't consider number of reads, we consider number of this unique molecule. So that goes into the UMI matrix. Okay, so that's the number at the end we will get. Okay, so the last slide is Cell Ranger will generate a report, HTML report, give you the estimated number of cells. Okay, in this case, this example is really it's pretty good. Normally we target to the 10,000 cells, maybe a little bit high, but this is already 15,000. If you get, say, 8,000, 6,000, don't feel surprised, will be okay. And that's the number of genes that detect medium level of each cell, how many genes have a greater than 0 expression. So you detect over 2,000, but a lot of cells have a more than that. That's mean numbers of arrays. So that's indication of the depths you sequenced. Because once you prepare this sequencing library, you can ask Illumina to give me, see, how many millions of arrays. If not enough, you can double it. Once your sequence library is prepared, you can always increase your depths if you don't have enough coverage. We have done this. Sometimes you see this saturation rate not high enough. We can, this is a little bit low. In this case, saturation. And in that case, we will increase the depths. Just ask to same library already prepared, and you can keep sequencing it to give you more coverage. Okay, this curve here, the log scaled, and then that's barcode. Remember, we have a long list. more than 700 of the barcodes. Then some of this barcode get some reads, but not enough. So that's indicate that's empty droplet. So some this empty droplet have very few UMI counts. That's definitely empty droplet. And there are some of this in the bound, in the gray zones, in the borderlands. So we have to set up a cutoff. See, any droplet has less than certain number of this UMI, I will count them as empty droplet. If above this cutoff, I think, okay, there's some cell in there. So we have to look at this curve, and a good curve will be have this annealing, and you have a drop certainly, so you know how to cut. If you have a curve like this, just gradually come out. So there's no clear cutoff place. That will be an indication of some low quality sample. You will get some curve like this. Okay, in this case, it's really clear. You have sudden drop of this UMI, so you have a clear separation of a droplet have cells and the droplet do not have cells. Then different version of this, and also the reference. So you needed to know, okay, how to read this and then whether it's good sequence or not. Okay, I think that's all. Leave the rest of time for questions. Remember, you need to know how to do this manually, and we will confirm you manual computation use MATLAB Thursday. And then know this, so treat the matrix as an operation and apply to vector. Vector is data point. So you change the data points to a new location. This new location could be on a straight line, still keep the same direction, or maybe rotated, scaled in different ways. And somehow you can explain the meaning of eigenvalue and eigenvectors. We will use that concept later. Okay, and now you should have a picture on your mind of how this pipeline works. Once you have a sequence FASTQ file, what to do and what's the step internally there. Okay, so just try to remember your key points, and we move on next week. Okay, Thursday we will still keep doing this analysis of real data. We can also play some of these operations to help you understand those. Okay. Any questions, online student and also in class students?